Hi, everybody, and welcome back to my Hanson Math YouTube channel. Today's video regards AP Calculus AB or Calc 1 straight line motion. In AP Calculus, it's section 4.2, and it regards straight line motion, also known as rectilinear motion, or motion happening along a straight path, either horizontally or vertically. I would put this on my Mount Rushmore of calculus, where this is a very, very important topic. So the first thing to note is that we're going to be looking at three types of functions. One regards position, one regards velocity, and the third regards acceleration. So the position function is often denoted with letter S, but sometimes it's also denoted with x of t. So it could be s of t, x of t. So time goes in and position of an object comes out. If you take the derivative of position, call it S prime, that's also known as velocity, because if you're looking at a graph of, let's say, time versus position, the derivative is position over time, which can be thought of as velocity. So the derivative of position is velocity. And then in turn, if you take the derivative of velocity, you get acceleration. So you can think of it as the derivative of position is velocity, the derivative of velocity is acceleration. So the second derivative of position is equivalent to the first derivative of velocity, which is equivalent to acceleration. They all do the same thing. Okay, these questions are extremely typical on the AP exam, so we'll start to look at them today. A handy little study guide for this is as below. We can talk about any object. This applies to any object. In this case, we're just being silly and we're talking about a bug, and the bug is only moving left or right along a straight path. That's all it can do. So we're going to translate some verbal statements into math, like physics or calculus. So if we say an object is stopped, like for example, a bug is stopped when its velocity is equal to 0. It has no velocity, it's not moving. A bug or an object moving to the right is defined as its velocity is positive. So we consider positive velocity moving to the right for these types of problems. Moving to the left is when the velocity is negative. Turning around means the velocity has a change of sign because you can't turn around without having a velocity of 0 first. So you have a sign change on either side of 0. So turning around is velocity changing sign. Speeding up is when velocity and acceleration have the same sign. So think about the wind. If you're moving in one direction and the wind is helping you from behind, you're going to speed up. So that's like sympathetic, the same sign. But think about slowing down. Think about if you were walking one way and the wind is blowing the other way in your face, that would cause you to slow down. So that would be different signs. So think about like opposing forces. If you're trying to go one way, but some force is pulling you back the other way, you would slow down. So the rule of thumb for calculus is an object is speeding up when acceleration and velocity have the same sign, and an object is slowing down when acceleration and velocity have opposing or different signs. We will look at this in the coming examples, starting right now. College Board and the AP test like to assess you via equations, via graphs, and via using the technology like a graphing application, and also using tables. So we'll look at a few of these right now. Okay, example 1 says, from time 0 to 8, we don't have units, so we just say from time 0 to 8, the position of a bug moving along the x-axis is defined by x of t, which is a position function. So this is a position function. How do I know that? One tell is x of t, and the other is that they flat out told us that it's a position function. So if you plug time in, position comes out. So for part A, what is the position of the bug when it first starts walking? Well, when it first starts walking is the beginning of the domain, which is 0. So we plug in 0 to the position function, x of 0 equals 1/3 times 0 cubed minus 7/2 times 0 squared plus 12 times 0 plus 2. Everything zeroes out here except for the 2. So the bug's position when it first starts walking is at 2. So think of it this way. If you were to draw a straight path like that, actually, I'll do it better. Okay, if you were to draw a horizontal line, all the bug can do is move to the left or to the right. So if you think about having an origin of 0, and then 1 to the right, and then 2 to the right, and then 3 to the right, the bug is currently at a position of 2, so the bug is currently right here. And it's right there at time equals 0. So as time marches on, think of like a metronome clicking, click, 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 click. As time marches on, the bug could either stay at position 2, the bug could walk to the right, or the bug could walk to the left. That's its only choices. Either stay put, move right, or move left. So right now, from plugging into the position function, we know the bug is at 2. Well, we can investigate some other questions, such as part B, at what times is the bug stopped? Well, if you look in your chart above, the bug is stopped when it has no velocity. That is when the velocity is equal to 0. And the velocity is the derivative of position. So if they start us with position, which is x of t, that would mean the velocity is x prime of t, okay? So since velocity is the derivative of position, so velocity is x prime, we have to take the derivative of this position function using the power rule. So the derivative of 1/3 t cubed is t squared minus the derivative of 7/2 t squared is 7t plus the derivative of 12t is just 12, and the derivative of this constant 2 is 0. Okay, so x prime of t is the same as velocity, and we're looking for when the bug is stopped or when we set the velocity equal to 0. So now we're trying to solve this. We're trying to say for what value of t or values of this velocity function is the outcome 0. So to do this, you could use the quadratic formula or you could factor. So we're going to try factoring since it's a quadratic. We're going to factor and set it equal to 0. So to factor t squared, we'd have t times t. We need what times what is 12 and adds to -7. So that's 4 and 3, both of which are negative. And then you solve to get 0 out. T could be either +4 or +3. Okay, so those are the two times at which the bug is stopped or not moving or a velocity of 0. So what this is going to instruct me to do next is I'm going to draw a number line like such. And on the number line, we're going to think about time goes in and velocity comes out. So time goes in and v of t velocity goes out. And the first thing I'm going to write on this number line is when was the bug stopped or not moving? So the bug was stopped or not moving at time 4 and time 3. So on my number line, I'm going to put in times. So we're going to have time 0 as a benchmark. Okay, down further, we're going to have 3, and we're also going to have 4. And it says here our domain is 0 to 8. So I'm going to put, well, I already put 0. And then down yonder, I'll put 8. Okay. So I didn't really need this other part. Our domain is from 0 until 8. Well, what did we establish from part B? The bug is stopped or has 0 velocity at time 4 and 3. So I'm going to note at time 3, the bug has 0 velocity, means it's stopped. And at time 4, it has 0 velocity, which means the bug is stopped. So this implies that the bug is moving from time 0 to time 3. Then it stops, and then it's moving from time 3 to time 4, and then it's moving from time 4 to time 8. But which way is it moving? Is it walking left or right? Because that's all I can do. Well, the question says, on what intervals of time is the bug walking to the left? So in order to do this, we need to use test points. And we need to do test points into the derivative, which could be this, or better yet, we're going to use the factored form. We're going to use the factored form. We already know what happens when we plug in 3 and 4. We get an outcome of 0, 0 velocity. So now what we want to do is we want to look at what is the sign of the velocity somewhere between 0 and 3 as far as time. Okay, let's say minutes, between 0 and 3 minutes. Well, a beautiful test point between 0 and 3, how about we plug in a 1. So if we plug in a 1 for t, here and here, we're going to say 1 minus 4 times 1 minus 3. Now, all I care about is what kind of sign comes out. 1 minus 4 is a negative, and 1 minus 3 is a negative. Negative times negative is positive. So if I plug in any number between 0 and 3, I get a positive outcome. And a positive velocity, right? Because we're talking about velocity. Positive velocity means that the bug is moving to the right by definition. Okay, so the bug is moving to the right. And then at 3 seconds or 3 minutes, it stops. Well, what's happening between the 3-minute and the 4-minute mark? Let's plug in another test point. What would be a good test point between 3 and 4? How about 3.5? So for t, we plug in 3.5. So 3.5 minus 4 times 3.5 minus 3. So now we have a negative times a positive. Negative times a positive is negative. So now we know any value between 3 and 4 will spit out a negative into the velocity function, which by definition means the bug is moving to the left. All right, finally, we need a test point between the bug being stopped at 4 minutes to 8 minutes. Any number between there will work, so how about 5? So if we plug in 5 into the velocity function, we have 5 minus 4 times 5 minus 3. And in this case, we get a positive times a positive, which is positive, which means that the bug has positive velocity on this time interval, which means it turns around and is moving to the right. All right, so now how do you answer this question? On what intervals of time is the bug walking to the left? It's walking to the left from time 3 to time 4. So my answer to the question is on the time interval of 3 to 4. Okay, that's all we need. How do I know it was the left? Because that was the interval of time in which it had a negative velocity. It would be walking to the right from 0 to 3 and from 4 until 8. Okay, now notice that this graph does not show its position. This was simply a graph of velocity, which tells you if it's moving to the left or right. All right, that was example 1. Example 2 is we're looking at a graph, and on this graph, the graph models the velocity. Okay, that's very important to pay attention to. What is the graph even modeling? So it says this graph models velocity. So the y-axis is velocity, and the x-axis is time. So this is a velocity versus time graph. So the y values literally tell you the velocity of the bug. So for question A, if it says, what is the bug's velocity at time 3? Well, its velocity at time 3 is just plug in 3 and you get out a 6. So its velocity at time 3 is 6. And its velocity at time 11 is right here, which is at a y value of -1. So if the graph is depicting velocity, the y values give you velocity. It's as simple as that. However, in part B, you're asked for A of 1, A of 5, A of 9. A refers to the acceleration, so we have to think, what is the connection between velocity and acceleration? Acceleration is the derivative of velocity. So since we're looking at the picture of velocity, acceleration is the same as the slope of the velocity graph. Acceleration is the slope of the velocity graph. So if I plot a point at 1, we're here. So we're looking for the acceleration is what is the slope on this path. So the slope is constant at up 2 over 1, up 2 over 1, up 2 over 1. So the acceleration at time 1 is 2. A of 5, at 5, we're right here. The slope there is flat as a pancake, which is 0. So the acceleration is 0, meaning the bug is not speeding up or slowing down. It's moving at a constant velocity of 6 feet per minute, 6 feet per hour, something like that. And A of 9 would be right here. When the time is 9, we're here. On that linear piece, our slope is down 2 over 1, down 2 over 1, down 2 over 1, which is -2. Okay, so if you're looking at a graph of velocity, the y values tell you the velocity, the slope tells you acceleration, because the derivative or the slope of v is acceleration. Okay, next question, C. At what time does the bug turn around? The bug turns around by definition. The bug turns around. We'll start with the reason. The definition of turning around is when the velocity has a sign change. So turning around is when the velocity changes sign. Okay, so let me clear off some of my scribbles here. So where does the velocity change sign? Well, if we track this graph here, we're starting with a velocity of 0. The velocity of the bug is positive all through here. Here it's positive and not changing, and it's still positive all the way until we get to time 9. At time 9, the velocity changes from positive to negative. Okay, so everything in yellow is positive velocity, everything in red is negative. So the bug turns around when the velocity changes signs on both sides of 0. So here we have positive velocity, and then it flips to negative, and that occurs at time 9. So this happens when t equals 9, and again, the reason is because velocity changed sign from positive to negative. All right. Okay, next, on what interval does the bug have negative acceleration? Well, acceleration is the derivative of velocity. So negative acceleration, we're looking for where v prime of t is negative or less than 0. So one way to think about this is if we're looking at the graph of velocity, acceleration is the slope. So we're looking for where is the slope of v negative. Okay, that's what we're looking for. Where is the slope of v negative? Okay, so we'll look on our graph. Where is the slope negative? Well, here the slope is positive. Here the slope is 0. Here the slope is negative from here all the way down until here. That's all negative downhill slope. And that occurs from time 6 up until time 10. So our answer is, on what interval does the bug have negative acceleration? That's on the interval from 6 until 10, because that's the times in which the slope of v is downhill or negative, from time 6 all the way downhill into time 10. Okay, next, part E. How many times is the speed, and speed is the key word, how many times is the speed of the bug equal to 2? Well, you got to be careful with the word speed. Speed means the absolute value of the velocity, because speed strips away direction. Speed is just the magnitude, not the direction. So speed is the absolute value of velocity. So since speed is the absolute value, if they ask you for a speed of 2, the velocity could be 2 or the velocity could be negative 2. So our velocity is 2 here, and our velocity is 2 here, but the velocity is negative 2 here. So there's 3 times in which the velocity is 2 or negative 2, which means the speed is just plain 2, just the magnitude, not the direction. So 3 times, 1, 2, 3. There are 3 times in which the speed of the bug is 2. Again, it means a velocity of positive 2 or negative 2. All right, I'm going to cut this video off and make a separate one of the next example. The next example is using technology to solve straight line motion. Thank you very much for watching this video, and I hope it helped, and stay tuned for future installments of HansonMath.com. Have a great day.